So I got cut off trying to finish this example of neutralization reactions, so we'll backtrack a little bit. We were going to work this problem out here, where we have nitric acid, HNO3, and barium hydroxide. All right, and when we combine this acid and base, the hydrogen from the acid and the hydroxide from the base will combine to form the water, H2O, and the nitrate ion and the barium ion will combine to form the salt. So barium has a 2+ charge and nitrate has a 1- charge. So if we do the crossover technique, that means we need 2 nitrates for every 1 barium. So the salt that forms is therefore barium nitrate. So you may need to freshen up, do a little refreshing on your ionic compound formation rules. So now we have the correct products, water and the salt, the proper salt, but what we're left with is an imbalanced equation, because on this side we've got 1 nitrate ion and over here we have 2 nitrate ions. All right, we have different amounts of oxygens and hydrogens as well. So I'm going to start by balancing that nitrate. If we have 2, if I put a 2 here, then we have 2 nitrates and 2 nitrates. Now let's look at barium is balanced. Let's look at the hydrogen. So we've got 2 plus 4 is 6 over here, and we've got 2 plus nothing, so we've only got 2 hydrogens over here. So if I add a 3 here, now I have 6 hydrogens. And now let's check our oxygens. We've got 2 times 3 is 6, plus 2 is 8 oxygens over on the reactant side, and we've got 3 plus 6 is 9 on the product side. So I'm not balanced. Did I count wrong? I counted wrong. Shoot. Okay. 2 times H. 2 H's plus 2 H's is 4 H's. I have 4 hydrogens on this side. So I only need to put a 2 here. So this should say 2 H2O's. All right. And now I have 2 times 3 is 6 oxygens plus 2 is 8 oxygens, and 2 plus 6 is 8. Okay, so now I am balanced. All right, so it's easy to make mistakes. Go back and double check, redo your counts. So the key here is the first thing you want to do is write out the products. So step 1 is write out the water and the salt, the correct formation of those products. And then if you need to, add coefficients to balance the equation. All right, so try these 2 on your own and check your answers. I will write them out here. So we've got the hydrogen and the hydroxide here are what are going to form the water, and the salt will be from the bromine and the lithium. Lithium bromide, because lithium has a 1+ charge, and bromine has a 1- charge, so it's a 1-to-1. Everything is balanced. I don't need to add any coefficients. In the second one, this H and the OH are going to combine to form H2O, and the salt is going to be from the calcium and the bromine. Calcium has a 2+ charge, bromine has a 1- charge, so it's going to be calcium bromide, CaBr2. And I will need to add some coefficients here to do some balancing. I've got 2 bromines, so I need to put a 2 here. And now I have 2 hydrogens plus 2 hydrogens, 4 hydrogens, and 2 oxygens. So now I'm balanced. All right, add a couple of 2 coefficients. Alrighty, to page for. Here we go. Alrighty, so for acid-base titration, we're sort of getting into a new topic here that still has to do with these neutralization reactions. So neutralization is involved in a buffer because you have a weak acid and a weak base, and they will neutralize any added acid or base. All right, and so we can use that sort of concept of neutralization, not just to create buffers, but to determine concentrations of unknown acids and bases. And this is a technique, a very commonly used technique in chemistry called titration, acid-base titration. So this is a technique that uses a solution of known concentration in order to figure out the unknown concentration of a second solution. So normally what you have, the setup is you have a flask with a solution that has an unknown concentration. In this scenario, the unknown solution is an acid, has a whole bunch of H plus in there. And so the known concentration, this is our titrant, the thing that goes in this large tube up here, is called the titrant. The known solution is the titrant. And it's going to be a base. And when we add the base, all right, it's going to neutralize the acid. So the OH minus will react with the H plus to form water molecules. All right, but there's still some H plus in there. So we add base, we keep adding that titrant until we have completely neutralized the solution. All right. If we keep going, then we'll end up with excess amounts of base, and that's not so good. So this right here is where we have reached what we call the equilibration point, or the equivalence point, I should say. This is the equivalence point. It's the point when the moles of hydrogen equal the moles of hydroxide. And we have completely neutralized, since the hydrogen and the hydroxide react to form water, we have created a neutral solution. It's all water. Okay? So a very common way to monitor the pH, now you can use a pH meter and monitor the pH that way, but a very common way to do this is to use colored dyes that are called pH indicators. And it's the same thing that we use with pH paper, basically contains some of these dyes so that it changes color when it reaches a certain pH. All right, so there's different types of acid-base titrations depending on the strength of the acid and base that we're using. So let's talk about the first type of acid-base titration, if we have a strong acid and a strong base. All right, when we do a titration, in this case, let's say we are starting with an acid, so the initial pH is going to be low. All right, this will be the initial pH of 1. All right, because there's a lot of H plus around in an acid. All right, and as we start adding base, the volume of the base increases. All right, initially there's going to be very little change, but as the amount of base goes up, as we get closer to that equivalence point, the pH is going to rise up very quickly, and then it will plateau out again. So at this point down here, all right, we still have an excess of H plus ions, which is why the pH stays very low. All right, and then up here, the pH is high because we have an excess now of OH minus ions. All right, and I should say that this in this titration, we are using, let's say, 0.1 molar hydrochloric acid. We have 25 mils of it in our flask. All right, and then we're titrating it by adding sodium hydroxide. And in the end, it will form water and sodium chloride, which is a neutral salt. So it should be a totally neutral pH at the end point of this titration, or in other words, when it's completely neutral. So during this if we do this titration beyond the titration point, so right here is where we ideally want to stop. All right, if we kept going, we would get this quick jump up to a very high pH. All right, so the initial pH, 0.1 here, all right, of the strong acid solution is right here. So for example, we have 0.1 molar hydrochloric acid, and the pH of that solution would be the negative log of 0.1, which equals a pH of 1. Hence, that's what we've marked on this graph here. All right, so before the equivalence point, all right, in this part right here, all right, the H plus is in excess, and we can calculate the concentration of that and the pH at these points by subtracting the moles of hydroxide that we've added from the initial moles of the hydrogen ion concentration by dividing the total volume. So let's look at that. All right, so in this case, if we have, let's do an example. What is the pH after adding 10 milliliters of sodium hydroxide? All right, so let's figure out first how many moles of sodium hydroxide did we add? And we can also figure out how many moles of H plus we had. So we will subtract the moles of OH from the moles of H plus. So if we added 0.01 liters, that's 10 milliliters is 0.01 liters, and the concentration of that sodium hydroxide is 0.1 molar or moles per liter, then that means that we added 0.001 moles. And for the moles of hydrogen, we have 0.025. This was our volume, 25 milliliters. So that's 0.25 liters, and the concentration is 0.1 moles per liter. So we have 0.0025 moles of H plus, and this is our number of moles of hydroxide. So after adding, so what happened was that we had 0.0025 moles of H plus, but 0.001 moles were neutralized by that hydroxide and turned to water. So we subtract that and we get 0.0015 moles of H plus are left. After adding 10 milliliters of NaOH, this is how many moles of hydroxide we have left. So the pH at that point will be the negative log of 0.0015 moles over the volume, the concentration here. The volume now is going to be 10 milliliters plus 25 milliliters, which is 35 milliliters. So 0.035 liters. That is our concentration. It's the log of the concentration. So the pH is the negative log of this, which is, if we do the division, it's 0.043, and the negative log of 0.043 is 1.37. So not that much higher than 1, which was our initial concentration. So you can see why this line stays somewhat flat. It goes up, the slope is very shallow because that concentration actually just goes up a very slight amount. All right, so part 3 here, at the equivalence point in the center, that is defined as when the moles of hydrogen equal the moles of hydroxide, and they completely cancel each other out, and so it's completely neutralized in a pH of 7. All right, the equation for this, I guess we could write this in another way, that the molarity, or the concentration of the acid times the volume of the acid equals the concentration of the base times the volume of the base. Because concentration, moles per liter, times volume equals moles. All right, so the moles, basically we're saying the moles of the acid equal the moles of the base, but since in titrations we're working with things with concentrations and volumes, we can basically just rewrite this equivalency as the concentration of the acid times the volume of the acid equals the concentration of the base times the volume of the base. So, for an example, how much sodium hydroxide must be added to reach the equivalence point. All right, so we know in this problem we are given the molarity of the acid and the volume of the acid and the molarity of the base, and we need to find out what is the volume of the base that needs to be added to reach that equivalence point. So we plug in the molarity of the acid is 0.1 molar times the volume of the acid, which is set at 25 milliliters, times the molarity of the base, which is 0.1, and then solve for x, that volume of the base. And in this case, it's easy since they have the same concentration, they will need to have the same volume. So x, which is the volume of the base, is also going to be equal to 25 milliliters. We will need to add 25 milliliters of sodium hydroxide to reach that equivalence point. All right, but if these concentrations are different, then those volumes will also be different. All right, beyond the equivalence point, so if we went back to that other slide, all right, here's the equivalence point, but beyond that equivalence point, all right, there's an excess amount of OH. We can also calculate the pH at this point by calculating how much excess OH there is. And we do that very similarly to how we calculate the pH over here. So it's just that neutralization reaction. So we just need to know how many moles of OH we have and how many moles of H plus we have. And then we do some subtraction to figure out the concentration of whichever one is in excess. All right, so the moles of hydroxide are going to be, and in general, as we just saw, moles of something equal the molarity, the concentration, times the volume. All right, so the moles of hydroxide, I guess I need to give you an example, a problem here. So let's say, for example, what is the pH after adding 30 milliliters of NaOH? So we remember that the equivalence point, we added 25 milliliters, so adding any more than that would give us an excess of OH. So let's figure out how many moles of OH we have and how many moles of H plus. All right, so the moles of H plus is the concentration, which was 0.1 molar, or moles per liter, times the volume. In this case, the volume is 0.03 liters. We want to convert 30 milliliters into liters so that our liters cancel. and we end up with 0.003 moles of hydroxide. All right, now moles of hydrogen, we had 0.1 molar, or moles per liter, and we had 25 milliliters in that flask. That's what we started with. We'll always have the same amount of hydrogen here because we're not changing the amount of acid in the flask. We can change how much sodium hydroxide we've added. So I want to convert that to liters, 0.025 liters. So my liters will cancel out and we get 0.0025 moles of H+. All right, so that means we have more OH than we do H+. So if we do some subtraction, 0.003 minus 0.0025, because for each mole of hydroxide we have, that will neutralize 1 mole of hydrogen ion. So if we have an unequal amount, in this case we have an excess of 0.0005 moles of OH minus. So the rest of these moles canceled each other out. 0.0025 moles of each neutralized each other, and the remainder is 0.0005 moles of hydroxide. So the pH is going to be calculated. Well, it's easier to find the pOH first. So we'll do it this way. pH equals 14 minus the pOH. And the pOH is the negative log of 0.0005, which is, oh, wait, nope, I made a mistake here, because the pOH is the negative log of the concentration, all right, the concentration of OH, and this is not the concentration, this is just the number of moles. So the concentration is moles per liter, molarity, so we need to divide this by the volume, and the volume is 0.025 liters of acid plus the 0.03 liters of base that we added. So together, that's 0.055 liters. So the concentration of OH minus is therefore 0.0091 molar. 0.0005 divided by 0.055. So now we can find the pOH, which is going to be the negative log of 0.0091 molar. So the pOH is 2.04, and the pH is 14 minus 2.04, which is 11.96, which makes sense. It's basic. It's a high pH. It's up here somewhere. We are past that equivalence point, and it is a high pH. So even though we only added an extra 5 milliliters past the equivalence point, it becomes basic very fast. All right, so here is another titration problem. All right, another strong base and strong acid. We have 50 ml sample of 0.2 molar sodium hydroxide. So this is our sample. This time we have the base in the flask. All right, this is our 0.200 molar sodium hydroxide, and we have 50 milliliters of it. And we're titrating it, our titrant in this problem, thing that's in this tube up here. This is the acid, and it's nitric acid, HNO3, and it has a concentration of 0.15 molar. And we will add it slowly to that base in order to neutralize it. All right, so part A wants us to, so this is just sort of a multi-part problem asking us to calculate many things based on this information. So first we want to calculate what is the initial pH. So the initial pH is simply going to be the pH of that base by itself. And since it's a base, we can calculate the pOH. the negative log of the hydroxide concentration. And since we have 0.20 molar sodium hydroxide, which is a strong base, it will simply dissociate into 0.20 molar hydroxide ions. So the POH is the negative log of 0.2, which equals I did my math wrong in my notes, so now I'm redoing it. .2 negative log of that is 0.70. So then the pH is 14 minus 0.70, which will be 13.30. So that is the pH of this initial basic solution. Now calculate the volume of acid that's needed to reach the equilibrium point. All right, so to reach the equilibrium point, the moles of acid equal the moles of base. All right, or in other words, the concentration of acid times the volume of acid equals the concentration of base times the volume of the base. So we know the concentration of the base is 0.200 molar, and the volume of the base is 50 milliliters. And the volume of the acid we don't know, but the concentration of the acid is 0.150 molar. So now we just solve for the volume of the acid, divide both sides by 0.150 molar. Molarities cancel out, and we end up with units of milliliters. So 0.2 divided by 0.15 times 50 is a volume of 67. Looking at my 67.6. All right, I need 3 sig figs, so 66.7 milliliters. Because initially I'm given 3 sig figs in all of these. So 66.7 milliliters of acid is what we need to add in order to have the same number of moles of hydrogen and hydroxide. And that is the definition of the equivalence point. Okay, so I'm going to write these answers in up here. So the answer to A is 13.30. The answer to B is 66.7 milliliters. And I'm going to do some erasing. There's some more space on the next page for you to do work, but I want to kind of keep it all together. So I'm just going to erase this and do part C. And I'm going to run out of time and have to do D, E, and F in the next video. So the next thing is calculate the pH at the equivalence point. So at the equivalence point, we have 66.7 milliliters of 0.150 moles per liter of acid. All right, so this will tell us our moles of acid. 66.7 times 0.1. Oh, wait, why am I even doing this? Okay, I can do this. Since this is a strong acid and a strong base, by definition, we're going to have equal moles of each. So we'll have, what is it, 10.005 moles of the acid, and we should also have the equal amounts of the base. So we have 50 milliliters of 0.200 moles per liter of our hydroxide, and it should be equal, and therefore